Hello everyone, welcome back to Triple Play Analytics. My name is Sasank. Today we're going to be looking at my newest sports model. It is on NHL shot effectiveness. So without further ado, let's jump on into it. So this model is located on my personal website. The URL is up here. I'll also put a link down in the description below. So before we start looking exactly at the model, what it does, its effectiveness, how accurate it is, and what it can tell us analysts and also casual sports fans and teams, I want to talk about kind of how I built the model, the thought process behind it, which can help explain certain tendencies the model shows and some biases that the model has actually avoided. So to start, we can see that there are a few libraries I loaded. I wrote this all in R, the R statistical programming language. The biggest package out of all these that's necessary is Caret. Caret is a collection of machine learning packages. So Caret is a package of packages. It is very, very dense. It has a lot of really good packages for machine learning. With that is the do parallel package. Do parallel, what it does is it parallelizes computation so that whenever we're training the model or doing any heavy computation, R can do it in parallel, so it would be faster, more efficient. ggplot2 is used to help make some nice graphics, and knitr or knitter is used to just make some nice visuals that you can see here. So first we get our data from the Money Puck play-by-play data. We're using data from the 2015-16 season, which is right here, to the 2018-19 season, or the current season. Now, the current season data is only updated until about February. That is when I got the data on February 8th. The last update of this entire page was February 24th, excuse me. Now, I'd like to tell you all, this model is still being worked on. I'm still fleshing it out and adding more features to it and making it a bit more responsive, a bit more interactive. Now it's been a few weeks just because I've been very busy with school and everything, but don't worry, more will be coming to this model. But right now, the basic idea and really the core part of the model has been created, which is extremely important. So we're going to be only looking at regular season shots. The playoffs is a completely different beast in the NHL. Playoff game-by-game information usually is different than regular season game-by-game. So we're going to be looking at a few different values from the Money Puck data. We have the X and Y coordinates from when a shot is taken, the angles taken on net, the distance from the net, the team, so we can sort a little bit, and also the shot type. This is the most crucial part, this type here. Now, I'd like to tell you all, with the X and Y coordinate information, yes, we can calculate the angle and distance ourselves. However, Money Puck actually has readings on that, the actual readings. Instead of us calculating and maybe having an error, I'd like to use the exact information which Money Puck gives us. So then we subset all our information. Now, before we continue, I need to explain what the shot type is. So there are 8 different shot types, labeled 1, 2, 3, 4, 5, 6, 7, 8. So this is what in R we call a factor. A factor is information linked with a specific number or ordering. So 1 is empty. Usually what happens in empty is when, for example, there's a goal, but the player who shoots it doesn't actually score it. It's a opponent player who accidentally tips the puck into his own net, or in a clearing attempt accidentally shoots the puck into his own net. That's happened iconically in the Stanley Cup Finals. Detroit did it in 2008 or 2009, I believe. It happens, but it's not really a shot on goal for the scoring team. It's just a blunder by the defending team. Then we have backhand shots, deflections, slap shots, snap shots, tip-ins or tips, wraparound shots or wraparound goals, more often than not, and then wrist shots. So we have all of our data from 2015-16 to 2018-19. Now, to train the model, I'm going to be using the two from 2015 to 2018, not including the season. So from the 2015-16 season to the 2017-18 season. All that data, 3 years of shot data I'll be using, which is going to be in analysis.all. That's extremely important because that is a lot of data. And I want to predict, I want to kind of see and predict how accurate this model is with current day shots from this year. So let's take a look at shots from this year actually. The first shot on goal from this season, the 2018-2019 season, was actually a backhand shot by Montreal. That was, at an angle of 59.93 degrees, 21.95 feet away from the net. Or if we're going to plot this on a graph, we'd see it'd be at 78 and negative 19. And it was a backhand shot by Montreal. The next shot was then a shot by Toronto. Then we see Montreal having a lot of shots, and then Toronto returning. And we have around 1,000 rows. And we can see the last data I have is by Arizona. Arizona registering a shot in row 1,000 of analysis 2018. So, without further ado, I also have a statistic I calculate. This statistic right here is goal percentage. So that is the number of goals over the total amount of shots on net. So that is pretty much goals over shots plus goals, assuming a shot does not mean a goal. That's important because that can really help us understand really how often a team will score on average. If we keep everything else equal and just look at goal percentage, let's say the Tampa Bay Lightning have a 20% goal percentage. So that means for every 2 shots, they'll score 2 goals every 10 shots. That's really, really good. You usually don't see something that high, but that's what this statistic will allow us to measure. So now let us create the model. First thing we have to do before we actually start creating the model is to make a controlled model. We use something called a repeated CV. So what a repeated CV is, it allows us to repeatedly train the model by splitting up our data set, so analysis.all, into a certain number of random groups. So that number is going to be 5 groups. And we train it, and then we split up the data again, train it, we split the data again, train it, so on and so forth. We do that splitting and training method 3 times. So we train 2 models in this. The first is a neural network, and the second is a k-nearest neighbors. In the previous sports models discussion episode, I talked about neural networks and k-nearest neighbors. For those of you that are just initially watching, allow me to re-explain it in a bit more detail this time. A neural network was developed, I think, in the 1970s, really to look at how we can mathematically model the human brain, model the human neurons in our brains. So the way neurons work is it's via electrical signals or electrical impulses. Let's say we sense something or we begin to think of something. Initially, one neuron will fire. And one neuron, it'll fire towards maybe one other neuron or an array of other neurons, a more than one. So we'll say it fires to other neurons. That firing of an electrical signal is then processed by a neuron, maybe changed a little, might be changed to a higher electrical signal or a lower electrical signal, depending on what the neuron computes in our brain. And then it's fired to other neurons. Now, it's very, very rare we see where we see one neuron fires an electrical signal to hundreds of thousands, maybe even millions of neurons. The human brain has a lot of neurons, so we see a neuron firing to maybe a few hundred neurons. Well, the way we do that mathematically is by kind of doing a weighted sum, and where each weight is kind of a node, per se. So let's say we start by reading our data in. It has to be numerical data. We read our data into kind of a node. Each node will then compute something on it. What usually happens is called a sigmoid function. It's 1 over 1 plus e to the negative x. That's a sigmoid function. What that does is kind of normalizes our information. We compute the sigmoid of our input data, and then we send our exit value, that computed value, to another neuron, or a list of other neurons, which will do more computation, and then send it to more neurons, or nodes, and keep sending it back and forth. continuing down a straight line until we get to the very last one. That last one will have to take multiple nodes, what they take it all into one, and sum them all together, or do some sort of aggregating function. Most times it's a sum, sometimes it's a product, sometimes it's some crazy formula. But in this case, let's just say it's sum or additive. So we add all that information together and we output it. We have one output. That is how a neural network works. We take in information, we do a step-by-step computation, each computation building off of the previous one that occurs, and then finally we aggregate it all together to get a single output. In this case, we see our single output is called goal, or determining whether or not a shot on net was a goal. So that goal value is 0 or 1. It's binary value, or it is true or false. So let's say, for example, Sidney Crosby takes a shot on net. It has either two outcomes of that shot. It either scores a goal, or 1, or it does not score a goal. It could either be a 0 then. So when it doesn't score a goal, we can say, okay, was it a shot on net? That's a different statistic. Was it blocked? Different statistic. We're only focusing on determining if this shot was a goal or not. Now you see here I have minus type. Well, you might be thinking, well, you're not training this model to determine the type of shot. However, if we scroll back up here, we see that type num is right here. It is the numerical value of this data shot type. And if we remember, shot type is the type of shot, which is a factor in R, or a list that correlates to a number. So what I'm doing is I am forcing all of the data that we're going to be putting into this machine learning model to be numerical, to make sure that the model can, 1, train as fast as possible, and 2, actually work with numerical information. So that if I take a shot, let's say I have this model, and 3 years down the line I revisit this, and I feed it in the necessary information, x, y, angle, distance, team, type num. I feed in all the proper input information, it'll be able to give me a goal still. It'll be able to give me a probability that a goal is scored. So that is one model create. We create a neural network. The second model create is called a k-nearest neighbors model. So a k-nearest neighbors model is extremely cool because you add each data point in one by one in the model to train it. So we first start with our very, very first input point. So that would be the very first 2015-2016 data point. And we know, okay, that value is maybe not a goal. And we know it has certain integer values. Now the nice thing about using numbers is that all numbers have a distance to each other. For example, the distance between 3 and 1 is going to be 3 minus 1, 2. Minus 1 again, 1. Because there's one number in between 3 and 1. That'd be the number 2. So now let's say we have a coordinate, an xy coordinate. For example, we're trying to calculate the distance between 0, 0 and 1, 1. Well, that value is going to be 1 minus 0 squared plus 1 minus 0 squared, square rooted, using our distance formula that you learned in your algebra class or in your geometry class. We find that that value is the square root of 2. Now, if we do that in 3 dimensions, where we have 3 points, or 4 dimensions, we have 4 points, the formula still stays the same. It's the difference between the first and the second squared, sum all that together, square root it. That is the exact distance between 2 points in any dimension. The good thing is, all our values are numeric, so we can calculate the distance. And what k-nearest neighbors does is it calculates the distance from one point to all its neighbors, and it finds the k closest or k nearest neighbors. And then from those k values, it determines what its machine learning output should be. For example, let's say the near k is 10 in this case. Then, whenever I put in a data point, I calculate the 10 closest neighbors. So I calculate the 10 values that have the closest distance to it, and then I will base my output of this value on those 10. Let's say, for example, three of those points have an output of goal, and 7 don't. So what I would say is I would give it a 30% likelihood of that value being a goal. So most times the model will just say 0. It will output a 0. But remember, when we have our control here, we repeat it 3 times. That is how we get an actual probability out of a k-nearest neighbors model. We do it multiple times. So maybe the first time we get no goal, 0. The second time we get, yes, it's a goal, 1. And the third time we get no goal, 0. So we have 0, 1, 0. Now actually this happens 15 times, 5 times 3, because we train it 5 times per 1 repeat. So we get 15 of those, and we're able to calculate an actual probability value. The more numbers and more repeats you do, the more accurate, the more repetitions you'll get. However, the more repetitions you have, the longer it will take. So there is that trade-off when training the model and actually getting a very, very accurate output of the model. So now that we know what the neural network model and k-nearest neighbors model are, we can actually test them and see some of the outputs, kind of analyze and look at those outputs. So first, let's just look at what the 2018 data looks like. What we see here, the Montreal goal, the Montreal, Toronto playing. I believe the first goal was scored by Montreal that game on a wraparound shot. It was at a 56-degree angle with a distance of 3.6 feet at 87 -3, that point. We can continue looking. Toronto's first goal was on a snapshot from 29.24 or 25 if we round degrees at a distance of 28.63 feet. So that is 64.14 if you were to plot that point. And we see here it's a goal. So now, let's kind of look at, let's just remember what value this is. This is 13, row 13 for the Montreal goal, and row 24 for the Toronto goal. Well, let's look at our neural network prediction. Row 13, this is a goal. This is our model will predict, the neural network model predicts that it has a 25% chance of scoring. Now in the NHL, most shots do not have a high probability of scoring. This has a 25% chance of scoring. That's extremely high. For example, this tip shot had a chance of 12.4%. This Toronto backhander had 18.6% chance. This 25 wraparound shot, that's extremely high. So that's a really good indication for that shot. And we've looked at 24. This Toronto snapshot had 5.86% chance of scoring based off our model. And this model only doesn't look at the player, it doesn't look at the time, it doesn't look at the opponent, it doesn't look at any of that. It looks at the shot itself. It doesn't even know the speed or the power of the shot. It doesn't know any of that. It just knows where it came from, the angle, distance, and the type of shot. And this had a 5.86% chance of scoring, so almost 6%. That's pretty high for a snapshot. We see here the next snapshot Toronto took had a 2.99%. We can see here that snapshots really don't have that high percentage shots because you can really predict where they go. They're that middle ground shot. They're not a slap shot, which can overpower a goalie with speed and power, but it's not a wrist shot that can really, really fool a goalie because of the pinpoint accuracy. A snapshot is kind of the middle ground between those two. And it's not a backhand shot, which can really throw a goalie for a loop given the deception a backhand shot has. It's not a wraparound shot either. The wraparound, the leading reason players take wraparounds is because if the goalie does not have good lateral or horizontal movement, then a player can use that to their advantage by going around the net and forcing the goalie to try to move right to left or left to right in enough time. Very skilled players can do that very, very quickly and catch a goalie off guard. For example, Connor McDavid, Brian Rust, who is extremely fast. Dylan Larkin, who's extremely fast, can do this as well. Players like this. Now, this is for the neural network. If we look at our K nearest neighbors, we see here this wraparound shot, it says has an 11% chance. This wraparound shot that scored had an 11% chance by the K nearest neighbors model. That is much less than what our neural network said of 25%. If we look at 24, this Toronto snapshot which scored had an 8.3% chance. Our neural network model said it had a 5.86% chance. So we see here that the models may, because we're only looking at 2 data points for both, so a small sample size, the models may show some differences. That's important to note because the models are meant to be different. A neural network is meant to be kind of like our brain. A K nearest neighbors is kind of looking off of the neighbors and kind of seeing similarities between shots. And so we can start visualizing these. And I want to first, before we start looking at the visualizations of what the model shows, I want to look at the frequency of these shots. So for example, here is the Pittsburgh Penguins and their frequency. We see the Penguins are a very wrist shot heavy team. That's important to know because that's primarily how a lot of their goals come from. But also we see backhanders are almost equivalent to tips, and slap and snap shots are pretty similar. Now if we go look at their rival, the Washington Capitals, we see wrist shots are pretty high, but unlike the Penguins, they have a higher amount of slap shots than snap shots. Also their backhand shots are not as frequent compared to the others. Let's look at, maybe the Calgary Flames. The Calgary Flames do not have as many shots in total compared to both the Capitals and the Penguins. They are not a high shot volume team. But we can see here, their wrist shots still heavily outweigh all of their other shots. So now let's go back to Penguins and take a look at their K nearest neighbors. Where did I put it? Right here. K nearest neighbors goal probability versus distance. We can see here that the K nearest neighbors plot, as we move farther away from the net, we see it kind of quadratically go down. But then it levels off as we get to 25 feet, and then it decreases more and starts to increase a little bit. Well, as we see here, this gold kind of covering or spread that we see on this black line, that tells us the variability. So we see that the model is pretty accurate, pretty happy, pretty accurate. Then it gets more variable, so more unsure. And it increases the uncertainty as we continue. That makes sense, because shots from further out should have higher uncertainty. Now we can take a look at another team, like the Washington Capitals. Washington Capitals follow this pretty closely. Follow this idea very closely. That should make sense. Teams should follow this. We can look at the Philadelphia Flyers, another team in that division. We can see that maybe that the probability when they go further doesn't increase as much as it did for the Penguins and the Capitals. Maybe because shots from out here are more likely to be empty netters. Maybe they don't have a high enough frequency of those. Or maybe they're just not as accurate when they're shooting at empty nets. We can take a look at the Colorado Avalanche, a team in the West. We can see here that they're close to the Penguins, but we see that this drop off here where it kind of plateaus for the Penguins and Capitals doesn't exist as much for the Avalanche as it does for the Penguins. So if we remember what this looks like here, we see it kind of slope down a little bit more. Let's go back to the Penguins, and we see it's flat. It kind of just flattens off. That's important to notice because some teams have different tendencies. Our models allow us to see that. So now let's look at this. This is the it's almost a bar graph, but it's kind of a density bar graph. This graph here shows the predicted goal or the probability we calculate from our model versus the shot type. So we can see the density given how many shots are there. We can also see the probability given how high it goes. So we can see here some of the Penguins' shots, like snapshots and tips, and backhanders have very high probabilities. But then some shots, like our wrist shots and slap shots, are very, very dense, which will, if we calculate the average of these, bring the average down. For example, the average slap shot, we see that their highest probability is a bit over 0.2, kind of almost 0.25 or 25%. But we see a lot of the density happening around here, near, in between 0.0 and 0.1. So maybe 5%. I'd probably err on the side of 2 to 3% on probability of scoring. So we see the weighted average here might be close to arguably 5, 6, maybe 7%. Now let's look at the Washington Capitals. Because the Washington Capitals are a rival of the Penguins, but we see here the slap shots, they have higher probabilities. They have a higher range of probabilities. Washington Capital players are a bit more accurate, or at least have more powerful, or have a better chance of scoring on a slap shot on average than the Pittsburgh Penguins. And that makes sense, given how the Capitals are built. Some of their players just have really, really good slap shots. For example, Alexander Ovechkin. So I'd like to finish this off by talking about where the future of this model will go. So this model is currently in its elementary, or it's very, very, very basic so far. I'm going to be working and adding more variety to this model. For example, you'll be able to view a specific player and how that player does with certain shots, or a specific goalie and how the goalie reacts to certain shots. Saying, for example, let's look at Carey Price. What is Carey Price's expected weakness shot? Is it wrist shots? Is it slap shots, snap shots, backhanders? Or, for example, for Austin Matthews, what is Austin Matthews' best shot? What is he expected to score most with? Most people would argue it's a slap shot, or a wrist shot. I'd argue it's not a wrist shot or a slap shot, as I misspoke. I argue it's a snapshot, actually, because he's extremely accurate with that. Some other players, like Alexander Ovechkin, we can easily guess slap shot. Sidney Crosby, I'd argue it's a tip or deflection, not a backhand, though he is most famously known for his extremely good backhand shot. So I'd like to wrap this up by informing all of you that we have a new Instagram account. It is just like the Twitter account at TryPlayAnalytic. We'll be doing PRing new upcoming videos like this one and new 100-word analyses, as well as I'll be posting some graphs for you guys to see, for you all to really see some really interesting information, interesting trends, whether it be baseball trends for like specific pitchers, or just in general trends for specific teams. Could be baseball, football, basketball, hockey, any of the big four North American sports. So I'd like to thank you all for watching, and I will see all of you around.